So we spent several days going over the Schrodinger equation, understanding the wave nature of the electron and how that shapes how the electron clouds can form around a nucleus. So now we're going to move on from the math and the physics to say, how does this actually affect the chemistry? So how we're going to approach this is, how do these equations manifest in the periodic table? So even before understanding what an atom even was, Mendeleev and others, Lothar Meyer was an important one, noticed patterns in the behaviors of the elements and organized the periodic table to give predictive power. Dmitry Mendeleev and Lothar Meyer were two of the people who did the most in organizing the periodic table. So some of Mendeleev's predictions, and so what Mendeleev particularly did was make these predictions that there'd be something he called eka aluminum beyond aluminum, and he pretty much nailed exactly the properties of gallium, the atomic mass, the density, and the reason the atomic mass is different is just because of the number of neutrons. Exactly what neutrons would be stable. Particularly the density, they would have a low melting point. Gallium has one of the lowest melting points of all metals. What the oxide formula and density would be, where it would be soluble, the formula of the chloride, and then it would be volatile. I mean, a lot of pretty impressive predictions. So there's clearly patterns in here, and what we want to do is use what we've learned about the quantum mechanics of the hydrogen atom, which generalizes into the other atoms as well, because they're also electrons going around a nucleus, and see how that creates the periodic table that we have, and starts to explain the behavior of the atoms in the periodic table as well. Okay. So the solutions to Schrodinger's equation explain all of these patterns. So learning objectives for this segment is to explain the reason for the Aufbau principle and what Aufbau actually means. Explain why the energy levels are not degenerate in multi-electron systems. Why are the 2s and 2p energy levels don't have the same energy? What are those orbitals not the same energy, where in hydrogen 2s and 2p have exactly the same energy? Explain the shape of the periodic table in terms of this Aufbau principle, and predict electron configurations using the principle. Okay, so remember, quick review of important concepts. The Schrodinger equation for the quantum mechanics of electrons gives us a series of mathematical functions, we call them wave functions, that tell us where the electron is likely to be. What is the probability of being in each region? Those are the only possible solutions for an electron around a nucleus. And we label these solutions with quantum numbers: principal quantum number, angular momentum quantum number, magnetic quantum number, and the spin quantum number are labels for the different solutions for where the electrons can be, and each of them have well-defined shapes. We know the functional form, we know its formula, we know where the probability is going to be. And we get 2 electrons per orbital, each with a different spin because of the Pauli exclusion principle. You can't have any two electrons that have the exact same quantum numbers. Okay, so the energy levels of the orbitals in hydrogen, as we've seen before, 1s is much lower, then up to 2s, 2p, and everything with the same principal quantum number has exactly the same energy. They're all the same, all energy is a single shell, same energy levels as the N in the Balmer-Rydberg equation. That equation we showed before, it's exactly the energy levels here. So right off, you can see patterns in the periodic table. Well, we have lots of sets of 2 that are similar, sets of 6, sets of 10, and then way at the bottom, once we get down to really big atoms, we get sets of 14 that fit together. So clearly, this is something that has some bearing, it's connected to the orbitals and how many there are. But the question, I think, is why isn't the periodic table like this? Why don't we have, first the 1s electrons, hydrogen, helium, then all the 2 electrons, 2s and 2p's, everything the second principal quantum number, right? Because those should be about the same energy. And then everything in the third quantum number, all the s electrons, all the 3s electrons, then the 3p, and then the 3d. That's sort of what you would expect. I mean, it's still periodic in the sense that when we stack it like this, everything in the same column has the same behavior, but it's not what we see. We don't see the patterns like this. We see different patterns. Why isn't the periodic table like this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That behaves pretty much all right, and up through 18. But after that, things start going a little crazy. Instead of You know, in order to make it fit the pattern like this, we have to jump straight from 18 to 21, and then go to 19. This doesn't match up with what we see. We'd expect if you had all the ones together, the twos together, the threes together, this is what we get, but it's not. And so the reason is the s, p, d, f orbitals, they're not the same energy if there's more than one electron. If you look at these outer electrons, they're not just feeling the attraction from the nucleus that's in the Schrodinger equation for the hydrogen atom, they're also repelling from a bunch of these other electrons as well. So we have to take all of those other interactions with the other electrons into account. And that actually makes the problem much harder. You have to do a lot more complicated. You know, the math for the hydrogen atom was bad. The math for anything else is much worse. And in most cases, you have to resort to numerical solutions. Yeah, so what we see is that if you have an electron way out here, then it essentially has, you know, 2 electrons in between it and the nucleus. So it experiences a net charge of about +1, whereas if it's much closer, it experiences almost a full +3 charge. It's not shielded very much. We call it shielded because the negative electrons are shielding the outside electron from the positive charge in the nucleus. So because of these effects, with the other electrons, you don't have s, p, d, and f orbitals at the same energy. Getting into a little bit more detail, there's a couple different effects going on here. So one is we see the 2s electron, because it has these 2 nodes, has a bunch of density down here that is almost inside the 1s electron shell. Like it's feeling essentially all of the energy, or it's feeling much more of the nuclear charge, and so it's attracted much more to, it has more attraction to the positive nucleus and therefore lower energy. Then also you notice that the 2p electrons are on average a little closer to most of the electron density here. So they're actually, you notice that the, let's undo that a little. You can see that on average, the 2p electrons are slightly closer to the center of the atom than the 2s electrons. And so they're actually bumping into the 1s electrons as well. So it's pretty complicated. It's hard to disentangle all of these things, but it's very clear that the 2s and the 2p electrons are interacting with the 1s electrons in a different way. So perhaps the exact magnitude is not entirely clear, but it's pretty clear that they will interact differently. The same with the 3s, 3p, and 3d. You know, they have different shapes, and therefore they're going to interact differently with the other s electrons. For example, because the 3p and the 3d electrons are closer to the 1s, and both of the things occur here as well, that you get penetration. The 1s penetrates the electron cloud, sorry, the 3s penetrates the electron cloud more than the 3d and 3p. The 3p, because of that node, also penetrates more. And again, because on average, 3d and 3p are closer than 3s, they're repelling the second shell electrons more. So there's a lot of different effects going on here. And don't have to worry about exactly knowing why all of them are occurring, but it's because of the different shapes, they interact differently with inner electrons. Okay, so what we get up in the end is energy levels that look more like this. And these energy levels here, they're not to scale with the hydrogen energy levels, they're just relative energy levels here. And so in most electrons, what you see, the 1s electrons are still way lower in energy than the 2s, than the 2p, that's all the same. Well, it's not quite the same. The 2p are a little higher than the 2s. And then the 3s, then the 3p. So it seems like we got a simple pattern here, s, then p. And then it starts to get a little more complicated because the higher up you go in energy, the closer they are together and the more that weird effects can change the order. So first we get the 4s, and then before the 4p, we get the 3d. So it's the 3d are all the way up here. They're high enough in energy that they are actually higher in energy than the 4s. Then the 4p, then the 5s, then the 4d. So it gets complicated. And but the good thing is you don't really have to memorize that, because all you got to do is look at the periodic table and it'll tell you which electrons are lower and higher in energy in the given atoms, you know, when you add the atoms on one by one.